Hey everybody, welcome to AlgoExpert. In this video, we're going to be covering the merge sort algorithm. This is a super famous sorting algorithm. You've probably already heard about it. In fact, you may have even implemented it in the past. But it's super important to really understand it well for a few reasons. Number one, like I said, super famous sorting algorithm, just good to know it and know how it works. Number two, it's a very sort of fundamental example of a divide and conquer algorithm, which is sort of an algorithmic technique of solving certain problems. And so it's great to be familiar with this kind of algorithm. Number three, merge sort is actually quite difficult. There's one solution, which we're going to cover first, which is sort of the basic way of solving merge sort. But it's actually not ideal from a space complexity point of view. And it also doesn't sort the array in place, at least not the way that we're going to do it. Now, the second solution that we're going to cover today is a much more complex version of merge sort. It's going to be much harder to grasp conceptually, but it'll be much better from a space complexity point of view, and it'll sort the array in place. So we'll be returning the exact same array that we were given. So without further ado, let's dive into merge sort. I've got in front of me an unsorted array of integers. Now granted, the array could already be sorted, but here, for the sake of this example, we're obviously going to deal with an unsorted array. And so we've got this one here, all right, 8, 5, 2, 9, 5, 6, 3. So how does merge sort work? Well, I guess I'm going to give myself a bit of space by moving the array near the top here. And I'm actually going to write the indices of all of the numbers in the array above them so that we have them kind of easily or readily available. So it's going to be 0, 1, 2, 3, 4, 5, 6. So we've got an array of 7 numbers. And the way merge sort works, as the fact that it's a divide and conquer algorithm suggests, merge sort divides an array into two and then conquers those two halves, so to speak, or in other words, kind of solves the sort of merge sort problem, which ends up being just sorting, right? Sorts the two arrays that you've divided or that you've obtained by dividing the first array, and then sort of continuously does this, continuously divides those subarrays and conquers their subarrays. Okay, so in our example here, right, we've got 7 numbers, and we're going to divide them into 2 subarrays. So because we're dealing with an odd number or odd amount of numbers, our 2 subarrays will have different lengths, but that doesn't really matter. So the way that we would divide it, like in code, is we would take the first index, which happens to be 0 here. We'd add it to the last index in the array, which is 6, right? So we would do 0 plus 6, and then we would divide that by 2 and round whatever answer we got, like round it down. Imagine we had, 7 here instead of 6. We'd do 7 divided by 2, 3.5, and round that down to 3. But here we've got an even number, so 0 plus 6 divided by 2 is equal to 3. So the middle of the array is defined by the number 3, by the index 3. And so we're going to divide the array right here in the middle with one subarray of 4 numbers and one subarray of 3 numbers. So let me undo what I just did to give ourselves some space. And so we're going to divide the array into these 2 subarrays, one which is going to have 8, 5, 2, 9, and one which is going to have 5, 6, 3. Okay? Then we're going to recursively apply the merge sort algorithm on, or the merge sort technique, whatever you want to call it, on these subarrays. Whoops, I forgot a comma after the 6. Okay? So let's start with the left subarray, right? 8, 5, 2. We're going to divide it in half, and we're going to get 8, 5, and 2, 9. Okay. And I guess before I dive into the right portion here, the 563, because this is going to be a sort of recursive algorithm, right, as you can imagine, we're going to first dive all the way to the left, right, and cover everything in this sort of base case here in the left, and then work our way to the right. Okay, so now we look at this subarray here, 8, 5, and we divide it further into two subarrays of length 1. So we're going to have 8, and we're going to have 5. So once we've reached two subarrays of length 1, this is where the sort of second part of merge sort occurs. Because so far, all we've done is kind of continuously divide our array into two subarrays of equal or almost equal length. But once we get to this base case where we've got subarrays of length 1, we start to recreate new arrays, new subarrays, until we eventually reach an array of the length of our input array. So we create new arrays out of these subarrays, except the new array that we create is going to be sorted. And the way we sort it is we say, well, compare these two characters. Here we're dealing with only two subarrays of length 1, so it's very easy. But compare these two numbers, and whichever one is smaller goes first, and whichever one is bigger goes second, right? So now I guess first of all, let me give myself a bit more space. So I'll move these arrays up a little bit like this, and I'll move these up. So now I'll write in purple, right? We're going to have an array that's going to be 5, 8, right? And the reason I'm writing it in purple is because this subarray here is sorted. Like, we have sorted it, and we have guaranteed that it is sorted because we took these two subarrays of length 1. We said 5 is smaller than 8. It's going to go first, and 8 is bigger than 5. It's going to go second. So now we do the same thing with this subarray, 2, 9. Okay, so 2, 9 is going to be 2 and 9, right? Two subarrays of length 1. And now we create a new subarray where we recombine them, but we make sure that it's sorted. So we've got 2 and 9. Here, this time the subarray hasn't been altered from the first one here. Okay, so now what do? Well, we've got two subarrays here, 5, 8, and 2, 9, that we know are sorted. Because we know they're sorted, we can combine them into an array of length 4, like the one that we have up here, right? This subarray. We can combine them into a sorted subarray of length 4 by just comparing the first character or the first number in each of them, right? So if we keep like pointers pointing to their numbers, and we start at the first number, we can say, oh, okay, this pointer here pointing to the number 2 is smaller than this number 5. So when we create our new subarray here, we can put 2 first, and we can kind of move our pointer to point to 9. And now we can say, okay, 5 is smaller than 9. And we know that this subarray is sorted, so any number like 5 here, or rather, let me rephrase. We know that this subarray is sorted, right? 2, 9 is sorted. So if 5 is smaller than 9, and 9 must be smaller than any numbers that might come after it, right? This subarray here might have other numbers like 10, 11, or whatever. We'd know that they would be bigger than 9, so 5 must be next in this combined subarray. And again, because also 5, 8 is sorted itself. So we know 5 is the smallest number. In other words, at any given point in time, we know that the two numbers being pointed at by our pointers are the smallest numbers. 5 is the smaller one here, so we can add 5. Now we move our pointer here, compare 8 to 9, and 8 is smaller. So we have 8. And finally, we add 9, and we're done. And of course, when we actually code this out, you'll kind of, you'll understand the nitty-gritty details of how this is implemented. Here, I'm kind of glossing over it. I'm giving you the sort of conceptual overview. But so now we've got this combined array of length 4 that is sorted. And so now we go all the way back up to our array of length 3 here, 5, 6, 3. And we do the exact same thing on this subarray. It's important to realize, like, what have we done thus far? We divided our main array into two parts, right? These two subarrays, one of length 4, 8, 5, 2, 9, and one of length 3, 5, 6, 3. And then we kept doing that same thing of like dividing our subarray and then doing some other stuff, right? Dividing and then conquering, until we eventually got to this point where we have a subarray, which is our same subarray here, except it's sorted. 2, 5, 8, 9. And now we're going to do the exact same thing on this subarray here. So we're going to divide the subarray the way that we divided it. Remember, if we've got an odd amount of numbers, we're always going to have a bigger subarray on the left and a smaller one on the right. So here we'll have 5, 6, and we'll have 3, right? And then 5, 6 can be further divided into two subarrays, right? 5 and 6. And then 3 just stays the same because it's a single subarray. And so now we can recombine these two and sort them together. So this is just going to be 5 and 6. This one is just going to be 3. Then we combine these two together. Right here, it so happens that they haven't changed, right? Like this entire portion that I'm sort of circling in green is identical because they were sorted within themselves, these subarrays. But now when we combine them, obviously we're going to have 3, 5, 6. And so now we've got a different subarray than we had up here. Okay? And so finally, now that we've got two sorted subarrays of lengths 4 and 3, we can combine them into one final array. And so again, this is going to be 2. So maybe here I should go through the actual logic, right? We're going to put 2 pointers pointing to the characters. Let me scroll up to give myself a bit of space. So 2 pointers here. And we're building an array that's going to have the length of our input array. It's going to have the length of the sum of the length of this array and this array. And so we compare 2 to 3. 2 is smaller, so we put it first. We can move the pointer to the right to 5. 5 is bigger than 3. And we know that any number that comes after 5 in this array is bigger than 5 because this is sorted. Any number that comes after 3 is bigger than 3 because it's sorted here as well. So 3 is our next smallest number, and it comes next. Move the arrow to the right. Now we're comparing 5 against 5. So we can just pick one, right? And pick one. Maybe we'll pick the left one here. Move this to 8. 5 is smaller than 8, so we add 5. Move the arrow to 6. 6 is smaller than 8, so we have 6. And then move the arrow to the right, and now we're done with this subarray. So we can basically say, okay, any number that's remaining here is going to be added. So we'll have 8 and 9. Okay, and of course the pointer would move, and now we'd be done at this point. So maybe I'm actually gonna rewrite this array to have it look a bit better, because right now the numbers aren't very well spaced out. So we would have 2, 3, 5, 5, 6, 8, 9. And that would be our final sorted array. And as you can see, this is a brand new array, right? We didn't do this in place. We didn't actually alter anything in our input array. But that's not necessarily too bad, right? Maybe it's bad, but it's not necessarily too bad. We have sorted our array. And to recap one more time, the way that it worked is we started with an input array, divided into 2 subarrays, and then our goal was to sort these two subarrays, right? To sort these two subarrays to get these two subarrays here that are sorted. And then to merge the two sorted subarrays into one big sorted array. How did we accomplish that? Well, we accomplished that by applying the same exact logic to each of the subarrays, right? We divided this subarray into two subarrays, sorted them to get this, and then recombined them to get a sorted subarray of length 4, and did the exact same thing here on the right side. And so, as you can see, this naturally becomes a sort of intrinsically recursive algorithm. And the base case occurs when we get arrays of length 1. Because when we get arrays of length 1, we can no longer divide them. So the concept of dividing and conquering no longer applies, and we work our way back up from there. So that's merge sort. Now, let's talk about the complexity analysis of merge sort. What is the time complexity of merge sort? Well, let's think about it. On our first call to the merge sort function, right, we're going to have some kind of function in our code that's going to be merge sort, right? What do? Well, we take in our input array of length n. Here, n happens to be 7. We divide it in 2. So we create, at least for our implementation, we're going to create sort of 2 copies of the subarrays, 1 copy here and 1 copy here. So creating the copy is going to be an O of n operation, because we're creating a copy of length n divided by 2, and then a copy of length n divided by 2, roughly n divided by 2. So creating the subarrays is O of n. And then if we jump down for a second to here, when we have the sorted arrays and we merge them together, merging these two subarrays together is also an O of n operation, right? Because we're iterating through all of the numbers in each of the arrays, and when you add them up, that's O of n, right? Because each array has a length roughly n divided by 2, so O of n. So, okay, so we've got O of n up here for creating the two subarrays, and we've got O of n down here for actually merging them together once they're sorted. So that gives us a total of, so far, let's write it on the right here, O of 2n. And of course, we can drop the constant, the 2, so we've got a time complexity so far of O of n. That's just for the main call to the first merge sort, right? The first call to the merge sort method. But right now, we haven't accounted for the time it takes to then recursively call merge sort on the two subarrays, and to actually sort them and get all the way down here before we can merge them. Okay, so let's analyze each of those calls of the two sub-calls to the merge sort algorithm. Okay, so far, again, let me erase everything that I've written and repeat what I've said, or recap what I've said. So far, we know that on the first array, we've got O of n. On the first call to merge sort, we've got an O of n time complexity algorithm just for creating the two subarrays, the two copies of the subarrays, and then merging them together once they're sorted. So now if we look at the two subarrays here, for each of the subarrays, they're also going to have to make copies or create two subarrays, right? Like this subarray of length 4 right here with an arrow is going to create these two subarrays here. And that's going to be so I want to make sure that we're clear here. That's going to be an O of m operation, where m is the length of this subarray, but we know that the length of this subarray is n divided by 2, or roughly n divided by 2, right? Because like we divided our main array of length n into 2 to get these two subarrays. So this is actually O of n divided by 2, right? And then merging the two sorted subarrays, right? So when we've got these two subarrays that are now sorted down here, merging them is also going to be, 1, 2, 3, 4 operations. We're going to be iterating through two subarrays of length 2. So we're going to be doing an O of n divided by 2 operation, right? So, and since we can drop the constant, basically, like another way of putting this, I guess, let me just rephrase. Another way of putting this is we know that it takes O of n time to do the dividing and then merging at the first call of merge sort. So for these two subcalls, it's going to take half of O of n, right? So it's going to take O of n divided by 2 for this one, and it's going to take O of n divided by 2 for this one. So if you add them up, it's going to be O of n for this entire level here. Okay, so we can rewrite this as, O of n for this entire level without counting the time that it's going to take to then call merge sort recursively on all of the subarrays here. So now let's dive into the subarrays. How much time does it take for these? Well, again, we know that it takes O of n time for the top array, and for each of those, we've got 4 of them, right? They're roughly the length of our input array divided by 4, their lengths. So it's going to be roughly O of n divided by 4 plus O of n divided by 4 plus O of n divided by 4 plus O of n divided by 4, right? In other words, we've got 4 subarrays that are each going to take O of n divided by 4 to then divide them into further subarrays and then remerge those further subarrays into one, without counting the time that it takes to recursively call merge sort on them. So what I'm getting at here is that every level here is going to take O of n time. It becomes pretty clear. Once we get to the base case, right, each base case only takes constant time. Like, we do nothing in the base case. It literally only takes constant time when we're at the base case, because we just call the merge sort function on an array of length 1, and we just return that array. But how much time does it take total? Well, here, how many arrays of length 1 do we have? We've got n arrays of length 1. So again, this is going to be O of n, because we've got n arrays of length 1, each function call taking constant time, so O of n. Okay, so we've got a bunch of O of n's, and now we just need to add them up to get the total time complexity of merge sort. How many O of n's do we have? Well, this is where we can kind of think back to binary search, right? If you're unfamiliar with binary search, you may want to check it out right here on algoexpert.io. We kind of cover this there. But that's where the log of n is going to come into play. Because we divide each array in half, then we further divide them in half, and then we further divide them in half, we get log of n. And so we have a total of log of n O of n's, which ends up being a total time complexity of time equals O of n. Well, I don't have space here. Let me rewrite this. Time complexity, spoiler alert, is going to be O of n log n. So let me just write it in small, maybe here. Time equals O of n log n, where n is the length of our input array. Again, why? Because every sort of level here, conceptual level in the merge sort algorithm, takes O of n time. And then, how many levels are there? Well, you just keep sort of dividing the things in half until you reach the base case, right? Divide by half, divide in half, divide in half, divide in half. and you get, that's where log of n comes from. And so you have a time complexity of n log n. And the beauty about merge sort is that in the best case, in the worst case, in the average case, it's always going to be log of n, or n log n, because you're always doing the exact same things. Like, unlike quicksort, for instance, where sometimes you can have bad time complexity depending on, the way the pivot divides the array into subarrays. And here, if you're unfamiliar with quicksort, of course, go check it out right here on algoexpert.io. But in merge sort, you're always dividing exactly in half. So you always, in the best case, average case, worst case, get n log n time. Now, space complexity is a bit trickier. It's going to end up being, we'll say, roughly O of n log n. The reason I say roughly is as follows. So, in total, right, you're always creating new arrays. Like here, you're creating a new array of length 4, a new array of length 3. Then you're creating new subarrays, right? Then new subarrays of length 1, and then you're merging them themselves into new subarrays here, 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 here. So in total, right, the same way that, we can, we deduced that the time complexity was O of n log n, in total in the algorithm, you generate or you create n log n space because of all these arrays that you're creating. Okay. Now, you could argue that because this is a recursive algorithm, at any given time, you have a bit less space, right? At any given time, you have you call you call merge sort on this algorithm. It's going to go down to this subarray. Then it's going to go down to this subarray, then to these two subarrays, and it's going to merge them into here. And then, you're going to go back up here, merge, create this, create this, create this, create this, and then go back up. And so you're discarding arrays. You're sort of like no longer dealing with some subarrays when you're moving back to different sort of recursive calls. So one could argue that there's a bit less than n log n space taken up at once, right, at any given time. In total in the algorithm, you definitely allocate n log n space to create all these subarrays. You also have the recursive calls that take up space on the call stack, which is just going to be log of n space on the call stack because, we've got only log of n levels, which are going to be the recursive calls, right? Log of n levels, the same way that we had O of n log of n times for the time complexity. But so the space complexity is certainly going to be more than O of n, right? At least like in practice, it's going to be more than O of n because you are going to be creating all of these subarrays and you're going to have, roughly like this much at any given time. Maybe I should write in a different color. You're going to have roughly this much space at any given time in your recursive calls. So the space complexity isn't great. It's not O then. And that's where I want to kind of transition into the second solution that I'm going to cover here and say, can we do better? Can we do better than O of n log n for the space? And also, can we maybe sort this array in place? Right? Can we be given an array and sort it in place? And the answer is actually yes. And that's where, that's the solution that we're going to cover right now. So let me undo a bunch of the stuff that I did so that we can actually see what's going on. Let me erase our time and space complexity here. And let me grab all of our subarrays. And let's make them smaller. And we'll get rid of them now, erasing them. Okay, so this second solution is quite complex. And the only thing that it's going to allow us to do is get an algorithm that really, truly runs in O of n space. It's going to be the same time complexity, but O of n space. and we're going to sort the array in place. So by that, what I mean is we're only going to use one extra copy of the array. That's going to be the only auxiliary space that we use. One extra copy of the array. And so we're going to have this concept of our main array and our auxiliary array. So our main array, I'm actually going to use different colors for this. Our main array, denoted by M, is going to be this first array here, the input array. Our auxiliary array, which I'll denote by A, is going to be right here. So I'll write it, and I'm going to make sure to give myself space. So actually, let me grab our main array and move it even higher up here. Let me move this a bit up. So our auxiliary array, which I'll write in purple, is going to be identical to the main array at first. So 8, 5, 2, 9, 5, 6, 3. And like I said, denoted by A. So the way the algorithm is going to work here is we're going to call our sort of like some kind of helper method to our merge sort algorithm, passing in both of these arrays, and then every time that we call that method again, we're going to pass in a main array and an auxiliary array. The main array is going to be the one where we actually like sort stuff, where we actually put sorted values in it. And the auxiliary array is just going to serve like a different purpose. But again, stick with me or stay with me because this is really complex. I want to make sure that you understand how it works. Perhaps the best way for you to understand how it works is to actually just go through the implementation, go through the example. So the first thing that we do is we divide our array in half. So again, we add up, 0 and 6, the first index and the last index, divide them by 2, round the value down, we get 3, and we cut the array in half here. So we've got 8, 5, 2, 9 as one subarray, and 5, 6, 3 as another subarray. When we cut 8, 5, 2, 9 as one subarray, we don't actually make a copy of it like we did in the previous algorithm, in the previous solution. We just keep track of it with pointers. Like we keep track of it by saying, oh, it starts at 0 and it ends at 3. Okay? And what we do is we call our helper method that we originally called with these two arrays, this one, the white one, as the main array, and then the purple one as the auxiliary array. We call the same helper method with the subarray 8529, except again, we're keeping track of it with pointers. But this time, what we do is we pass the auxiliary array as the main array, and the main array as the auxiliary array. So right now, you're probably thinking, like, wait, what? What did you just say? So let's dive into it slowly. We pass the auxiliary array as the main array, and the main array as the auxiliary array. The way I'm gonna make this visually apparent is the top array is gonna be the main array that we deal with, like what the helper method considers to be the main array, and the bottom array is gonna be what the helper method considers to be the auxiliary array. But know that the white array and the purple array are sort of like initial main input array and auxiliary copied array. Okay, so now we have this 8, 5, 2, 9, and then we have 8, 5, 2, 9. Okay, so hopefully this makes kind of sense, right? We first called the helper method here, helper, right? Passing in these two arrays, The top one was what the helper method considered to be the main array, and it was our main input array because it's in white. And the bottom one was what the helper method considered to be the auxiliary array, which was exactly our auxiliary array in purple. Then we called the helper method again, right? Helper. Except this time, the main array, which is at the top, is actually our auxiliary array. And the auxiliary array, which is at the bottom, is actually our main array. Okay? So far, so good. Hopefully you're still with me. And you'll see as we dive more into it why this is needed. So now we further divide the arrays, and again we call the helper method, but swapping them back. So now we've got the main array here with 8 and 5, and then we've got the auxiliary array with 8 and 5. Okay? And now we divide them even more, right? We divide them even more. So right now we're at this call to the helper method. We divide them even more into two subarrays of length 1, so we would have 8 and 5. And we call again the helper method on, and here I'm going to write them a bit differently, on 8 and, or I guess on 8 and on 5, okay? We call the helper method twice on each of them. So helper and helper. Now, our helper method, as soon as it sees an array of length 1, as soon as we hit the base case, it's just going to return. It's not going to do anything. That's why I wrote them like this, and so I'm immediately going to erase them. Okay, we've hit the base case, there's nothing to do. Okay? And now we go back up, to this call of the helper method, where we're dealing with these two arrays, and we make a call to another method, which is going to be our actual, merge method, which we're going to call probably, do merge or something in the code. And that method is going to be in charge of combining subarrays into one sorted subarray. So remember, we're dealing, and this might be clearer when we get into the code, remember, we're dealing with pointers to indices. We're not actually dealing with copies of arrays. The only extra array that we have is this auxiliary array in purple here. So when we make a call now to this do merge method, what we're doing is we're passing indices. We're passing a starting index, a middle index, and an ending index. And that's how we know where our subarrays are. So our do merge method is essentially going to know that, oh, we actually have two subarrays that we want to merge now. We've got 8, which was hit in the base case of helper, and 5, which was also hit in the base case of helper. These are two sort of single subarrays. They are our base case. They are sorted as individual single number subarrays. Let's sort them into one sorted length 2 array. So what the do merge method is going to do is it's going to take in what we consider to be the main array in our current helper, which is the top array here, which so happens to be our actual white main array. It's going to take this as its main array, and it's going to say, this is where I'm going to sort values. And it's going to use the auxiliary array as the sort of subarrays that it's comparing. So it's going to say, okay, we've got two subarrays based on our pointers that we passed, 8 and 5. Compare their two values. 5 is smaller than 8, so 5 is going to come first. And so, I guess let me undo this, maybe make this more clear. Now we are in do merge here, and we've got a main array or a top array which happens to be our main array, and we've got an auxiliary array which happens to be our actual auxiliary array. And we're going to say, okay, let's merge the values based on our pointers in this auxiliary array into sorted order in the main array. Okay, so compare 5 to 8. 5 is smaller than 8. So we're actually going to erase the 8 here and write maybe I'll write it in like brown now. Write 5, and this is sorted. This 5 here is sorted, okay? And here probably we have 2 pointers here. Maybe I should make them different colors. Let me erase them. We've got 2 pointers here, and we compare these 2 values. We see that 5 is smaller, so we move the pointer out. We overwrite this value in the merged, or in the main array, sorry, to be 5. And then we're left with only 8. And so we overwrite the second value here to be 8. So we erase this, and we've got 8. Now let's take a pause here. And of course we move this pointer to the right, and now we're done with it. So what did this doMerge method do? It merged values that were in sorted order and they're in individual arrays in the auxiliary array into sorted order into a bigger subarray in the main array. So we got 5, 8 here. But so, because we're dealing with the same 2 arrays since the very first call to the helper method up here, the same 2 arrays being the main array and the auxiliary array, this 5, 8 here should be reflected everywhere in our white array here. So I'm actually going to erase 8, 5 everywhere here and replace it in brown with 5, 8. 5, 8, and 5, 8. Okay? Because the main array here, even though here I only represented 2 values, it's actually a full array of length 7, but we're just dealing with these 2 values based on pointers, right? And so it overwrites it in all instances, or all like places where we're dealing with the main array. Okay, so now let me erase this, and we'll start seeing where the rest of the algorithm is going. Let me erase this. Okay. Now we have this portion where, like, now we go back up to probably this helper method right here, this helper method, and we've divided our arrays into 2 parts, and we've dealt with this left part. So now we want to deal with this right part. Okay, so we're going to divide it into 2, 9. And this is going to be in purple, 2, 9. And again, in this helper method, our top array was the auxiliary array, our bottom array was the main array. But then when we call the helper method again down here, right? Now our top array is the main array, and our bottom array is the auxiliary array. And so now at this point, we call the helper method on 2, we call the helper method on 9. These are single number arrays, so we kind of hit our base case and we don't do anything. And now we call the doMerge method, right? doMerge, doM, which is going to, again, sort of overwrite the values in our top array here based on the values in our auxiliary array. And so it turns out that 2 and 9 are in sorted order. So the first value is going to be 2 and the second value is going to be 9. But we are like overwriting them, right? So I'm going to erase it here, here, and here, because these are all the places where we have our main array. And I'm going to write them in brown. 2, 9, 2, 9. Maybe I should also write the commas in white. Or in brown, sorry. Okay. So now, this is completely sorted. Okay, so now we move back up to the helper method here. The sort of, which one was it? Let's see. Oh no, so now, wait, so this is where it's tricky, right? You have to make sure that, like, you have to make sure that you're keeping track of everything. So, we had, now we're dealing with the helper method here, which called Yeah. So sorry. Let me rephrase. Right. This is really confusing. We had this helper method here, which I wrongly erased. Then we had the helper method here, which called doMerge. Right. DoMerge got done. This helper method got done. And now we want to call doMerge at this level, right? We want to call doMerge at this level here, okay? So the way that that's going to happen now is this doMerge here is going to take as its main array, or as its top array, let me write it not in white, it's going to take the top array here in this helper method, which is our auxiliary array. So it's going to take in as its top array 8, 5, 2, 9, and it's going to take in as its auxiliary array, as its bottom array, our main array, which happens to be sorted right now. So 5, 8, 2, 9, or not sorted, sorry, but it consists of two sorted subarrays, right? 5, 8, and 2, 9 are both sorted. And so now we're going to put, 2 pointers, one pointing to the beginning of 2, 9, one pointing to the beginning of 5, 8, and we're going to merge these two subarrays into what doMerge considers to be the main array, which here is the auxiliary array. And this is where we have to take a pause and here acknowledge that this is why we've done all this sort of complex swapping of auxiliary and main arrays throughout the entire time, because if we start overwriting values here, imagine we didn't have this auxiliary array. I guess imagine we did not have this. If we started overwriting values in our main array here, we could say, 2 is smaller than 5. So 2 should come first. And so we could erase this 5 and make it be 2. But then we'd lose track of the 5. Like, the 5 would be gone, right? And so that's why we need these two arrays. We always need one array to store, like, the sort of initial values, and we need one array to store new sorted values. And the way it works is you have to kind of continuously swap them. Okay? So let me undo this. And so here we can see that 2 is smaller than 5. So I can erase this 8 and make it be a 2. Then I can say that I can move, I guess, the 2 pointer to 9, and 5 is smaller than 9. So I can erase this 5, right? Or, sorry, erase this 5 and make it in brown because it's sorted. And then we move on to 8, compare 8 and 9. 8 is smaller than 9, so this 2 becomes 8, and then we're going to have a 9. So we've got 8 and 9. Now, it's important to point out, this is the auxiliary array, so every place where we've got the auxiliary array, we should have 2, 5, 8, 9. So now, this here becomes 2, 5. This here becomes 8, 9. This here becomes 2, 5, 8, 9. And so does this here. So we've got 2, 5, 8, 9. 2, 5, 8, 9. And so you can already tell, right? You can already tell at this point that when we get back up to the helper method at the very beginning, we're going to be calling doMerge with the main array here as our top array, the final array in which we're going to be sorting stuff. And we're going to be using these sorted subarrays in this auxiliary array. So far, we've only sorted one, this one here, right? And we're going to be using them to create our to sort our final array in the main array. So let me undo all of that. And now let's actually, let's just finish implementing this really quickly before we can dive into the code walkthrough. And the code walkthrough hopefully will make things clearer. But I will say that this is a very complex version of merge sort, which is why merge sort can be pretty difficult. So now we've got we've got the second half here, so it's going to be 5, 6, 3 as the auxiliary array, and then 5, 6, 3 as the main array. Though, again, here the main array is the second array, and the auxiliary array is the first one, the top one. Then we've got here 5, 6, and 3. And, well, I guess the 3 comes after, so let me erase it. And we've got 5, 6 here. And now we call the doMerge method, so we erase these and put them in sorted order. So we've got, 5, 6, and we have to erase them everywhere else. 5, 6, 5, 6, 5, 6. Then we've got our 3, which I guess can just come here, and it's in sorted order. So it's going to be, so this is going to be 3. We can erase it here and here. 3, 3. And now we want to call doMerge at this level, right? So doMerge at this level. So let me undo that. So now we're going to combine, 5, 6, which is sorted, and 3, which is sorted, and overwrite them here in our auxiliary array. So this is going to become 3, 5, 6, which means that this here becomes 3, 5, and here, 6, 6. And this up here becomes 3, 5, 6. And now finally we call doMerge up here, doM up here, and we take our auxiliary array and merge these values of these two subarrays right here, right? And merge them into our main array. And so this is going to end up being the sorted array, right? We're going to take 2 coming from here, then 3 coming from here, 5, 5 coming from here, 6, 8, 9. Okay? Okay, so this was a really tough algorithm. I think it'll make more sense now that if we dive into the code walkthrough. I don't want to overdo it with this conceptual overview. But so this is going to run in O of n log n time. It's the same because the logic from a time complexity point of view is exactly the same, right? We're kind of dividing and conquering. We have the same doMerge that takes O of n time, right? The actual doMerge portion is what takes O of n time. Everything else is constant time, right? Dividing the arrays into 2, we're not actually making copies, we're just creating pointers. So doing simple calculations. And then how many levels do we have? Or how many calls to the sort of merge sort helper function do we have? To the doMerge method do we have? Log of n calls. Okay, so O then log n, or roughly log of n. It might be log of n plus 1 if you count the root call. The space complexity, on the other hand, is unequivocally O of n space, because we only have one additional array, this auxiliary array. Like, even if in the other algorithm, like we said, it was like an upper bound was n log n, maybe in practice it was a bit less than n log n, but we definitely had more than O of n in practice, because we were creating all of these copied arrays. Okay, and the recursive calls only took up log of n space. But so here, the space complexity is undeniably O of n. And again, the recursive calls only take log of n space, so we can kind of drop the log of n. So it's only O of n. So with that, let's dive into the code walkthrough to really see how the two solutions, or what they look like, and hopefully to understand the second solution better. All right, so we've got our merge sort function defined. It takes in an array of integers. And for the first solution, the first thing that we're going to want to do is take care of our base case. What happens when we call merge sort with an array of length 1? Well, if the len of the array is equal to 1, we just want to return that array. Right? There's nothing to do in the base case but to return the array. If we're not dealing with the base case, if we've got an array that's bigger than just one number, then we want to divide it in half, or roughly half. So the way that we're going to do it is we're going to calculate a middle index, which is just going to be the length of the array divided by 2. And in Python, we'll use the double slash to round that value down. If you were writing this in JavaScript, you'd probably do math.floor, or you can use whatever tool is available to you in your language to round this value down, the length of the array divided by 2, because indices have to be whole numbers. So then we're going to create our left subarray, which is going to be sort of the left portion of our input array. And this is just going to be a slice of our input array. So we'll take our input array and slice it all the way to the middle index. And for the right half of the subarray, we will just slice it from the middle index, onwards. And of course, the middle index is either included or excluded in one of the two halves. It doesn't really matter which half you do. I think in the conceptual overview, we were always including the middle index in the left half, but it could go either or. It depends on your preference. And so finally, once we have that, we can say, well, okay, what do we want to do? We want to further divide these halves and further call the merge sort algorithm on these halves. So we know that we're going to call merge sort on these two halves, on the left half and on the right half. But then we also want to merge them together, right? So we need some kind of helper method. So what we can do is we can actually just say, hey, call the helper method. So we'll call it merge sorted arrays, right? Because ideally, like once we call merge sort on our left half and on our right half, we obtain sorted arrays, and then we just want to merge them together. So our helper method is going to be called merge sorted arrays. And we'll call it, passing it the result of calling merge sort on both halves. And so you can imagine that in the base case, right, when we hit the base case and we return arrays of length 1, merge sort of left half and merge sort of right half are just going to be both arrays of length 1 that are sorted because they're of length 1, and we merge them together. And so now we can actually write the helper method, which is merge sorted arrays. This takes in a left half and a right half. And the way that we're going to implement this is using pointers. Again, here there are various ways of implementing this method. The way that I'll show is one that I particularly like. So we'll create a new array, which is going to be our sorted array, and we're going to sort of continuously build up our sorted array based on the values that we compare in the left half and in the right half. So we'll create our sorted array to be of the length of the merged two arrays, because remember, we're merging them as the name of our helper method implies. So our sorted array can start out as just being filled with a bunch of random values, none values. So in Python, I'll just do none multiplied by len of left half plus len of right half. So what am I doing here? I'm saying grab the length of the left half, grab the length of the right half. That's going to be the length, add them together. That's going to be the length of our merged array. And create an array of just a bunch of none values. And you can do this however you want in your language of choice. Then we're going to declare three indices, k, y, or ki, and j. So k is going to be equal to I, is going to be equal to j, is going to be equal to 0. K is going to be the pointer, or the current index that we're at in the sorted array, and it starts at 0. I is going to be the pointer for the left half, and j is going to be the pointer for the right half. And so we're going to say, while I is less than the len of the left half, in other words, while we're still dealing with a pointer that's in the left half, so far as we still have numbers in the left half to deal with, and while j is less than the len of the right half, we're going to do stuff here. What is this stuff? Well, we're going to compare the number at the ith index in the left half to the number at the jth index in the right half. And then we're going to say if left half at index I is less than or equal to right half at index j, then sorted array at index k is going to be equal to left half and index I. And we're going to increment I by 1. So what am I doing here? I'm saying if the number in the left half at index I, which starts out as the first number in the left half, is smaller than or equal to the same number except at index j, or the corresponding number at index j in the right half, then make the number in the sorted array at index k equal to the left half. And increment I by 1, because now we've used up that number. Otherwise, right, then the number in sorted array at index k should be equal to right half at index j, right? And we should increment, in this case, j by 1. And in either case, regardless of if we're using the left half number at index I or the right half number at index j, we have to increment k because we've just filled up something in the sorted array, okay? So far, hopefully so good. By the time that we get out of this while loop here on line 12, we've either run out of numbers in the left half or run out of numbers in the right half, right? Because we're gonna eliminate one of the two subarrays first. And so here we can just add two other while loops to account for those conditions. If we still have numbers in the left half, which means that I is less than left half, then just set the sorted array at k to be equal to left half at I, and keep incrementing I by 1 and k by 1. And similarly, we can do the exact same thing for the right half. So long as j is less than the right half, sorted array at k is going to be equal to right half at index j, and we're going to increment j by 1 and k by 1. Okay? And finally, we can just return the sorted array. So let's recap what we did, because now we're done with the algorithm. We've got our main method, merge sort, takes in an array. If it's the base case, we return the array. Otherwise, we divide it in two, create two copies, a left half and a right half. These copies are copies of subarrays, right? And we call merge sort on these two halves recursively. Eventually, we get to the base cases. These merge sort methods return a call to the merge sorted arrays method, taking in those two halves, right? And so eventually they return sorted arrays, sorted versions of the subarrays, because the merge sorted arrays method takes in two halves, and the very first call to merge sorted arrays is going to take in two subarrays of length 1. It creates a new sorted array of the length of the sum of the lengths of these two halves. And with this little logic here, we sort of continuously compare the numbers in the left half and in the right half, keeping in mind that they're sorted, right? And we populate our sorted array. And eventually we return the sorted array, and that's how the algorithm works. So this is going to run in O of n log n time. You can add parentheses to log n just for clarity, right? O of n log n time. And roughly O of n log n space. Or at least we know that, like I said, we're creating all of these copies of arrays, and overall throughout the entire life of the algorithm, we are creating O of n log n additional space. And we're not sorting the array in place, right? We're not returning the same sort of version. We're not mutating our input array. Typically, when you sort arrays, you tend to mutate them, though, of course, like if you were in an interview, you'd probably want to ask your interviewer if that's a thing you have to do. But so now let's dive into the second version of this problem. So let me comment this out. Let's give ourselves a lot of space, and we're going to define merge sort a second time, taking in a simple array. And so the second version is going to be similar to the first one, right? If we are in the base case, right, we can just return our array. So if we're given an array of length 1 or smaller than 1, right, we can say imagine we're given an array of length smaller than 1, like an empty array, then we can just return the array. Okay? Otherwise, what we're going to do is we're going to create a copy of the array, which is going to be the only copy of our array. And this is going to be our auxiliary array. So auxiliary array is going to be equal to just a sliced version of our array. Okay? And now we're going to call our helper method. Remember that when I was going over the conceptual walkthrough of this algorithm, we had this helper method that I kept writing in green, and then we had the doMerge method. So here we're first going to call the merge sort helper method, passes in our array, the input array. It passes in an auxiliary array, and it passes in pointers to the start of the array and the end of the array. And since this is the first call to the helper method that we're dealing with the entire arrays, right? So our starting index is going to be 0, and our ending index is going to be the len of the array minus 1. Okay? Now, as we dive into the definition of the merge sort helper, we're going to start to introduce the concept of the main array and of the auxiliary array. The main array is going to be this first parameter, which starts out as our input array, and the auxiliary array is going to be the second parameter, which starts out as our auxiliary array. Okay, so let's define it. Merge sort helper takes in a main array, a starting index, an ending index, and an auxiliary array. And we can also here deal with the base case, which is if the starting index is equal to the ending index, then we can just return, right? We don't do anything. And the reason we don't do anything is, remember, we're not creating copies of arrays. We don't need to return values here. We're just saying, okay, we're not gonna overwrite anything. We're dealing with a single value in the array, right? Our starting index is equal to the ending index. Don't do anything. Otherwise, calculate the middle index. The middle index is going to be equal to starting index plus ending index divided by 2 rounded down. So if you remember during the conceptual overview, I said take the first index in the array, the starting index, take the ending index in the array, the last index, divide them by 2, and you've got your middle index. In the first call to merge sort helper, this is going to be 0 plus 6 in the case of our example earlier, divided by 2 equals 3, right? That's going to be the middle index. And then now we make 2 calls to merge sort helper, passing in the auxiliary array, but this time the auxiliary array as the main array, passing in the starting index and passing in the middle index. Here we're passing in the middle index as the ending index. In other words, we're kind of dividing our arrays into 2, right? And then we pass the main array as the auxiliary array. And we call this twice, except the second time we pass in middle index plus 1 and end index as the starting index and as the ending index. So you can see these indices that we're passing are effectively doing the dividing, right? And we're swapping the auxiliary array and the main array. So when this merge sort helper gets called here a second time, the auxiliary array, our original auxiliary array, will be our main array in the method. And then so on and so forth. When we recall the methods, the merge sort helper method, we're going to further swap them, right? So for this algorithm, I really encourage you, if right now you're still a bit confused, I really encourage you to either go back to the conceptual overview and really go through the example line by line, or the example kind of frame by frame when I was explaining it, or try to go through an example yourself, actually going through all the calls to the method and seeing how it works, right? That'll make things clearer to you. Finally, we call the doMerge method, and this time we pass in the main array. We pass in the main array that we passed. So here we don't do the swap. The swap is only for the helper methods. Pass in the main array, pass in the starting index, the middle index, and the ending index. And this is going to allow us to actually know how to delineate sort of the two, or separate the two subarrays in the doMerge method. And we pass in the auxiliary array, okay? And so now, if we define the doMerge method takes in a main array, it takes in a starting index, a middle index, and an ending index, as well as an auxiliary array. And the first thing that we want to do is declare our sort of indices, k, I, and j, similar to how we had them in the previous solution. So k is going to be the starting index. Why is k the starting index? Well, think about it. We're essentially merging two subarrays, one that starts at starting index and ends at middle index, and one that starts at middle index and ends at ending index, okay? So when we merge them into the main array, in the main array, we start at the first index of the first subarray, which is starting index. So that's why k is equal to starting index. I is also going to be equal to starting index, because the first index in the first subarray is also starting index. J, on the other hand, is going to be middle index plus 1, okay? Because when we called merge sort helper here, we called it passing middle index plus 1 as the starting index. So J is going to be equal to middle index plus 1. And now this is going to look very similar to the previous solution. While I is less than or equal to middle index, which middle index is basically the final index in the first subarray, and while j is less than or equal to the ending index. If, and we compare auxiliary array at index I is smaller than or equal to auxiliary array at index j, then the main array at index k gets overwritten to be auxiliary array at index I. So again, you can see that we're comparing values in what was in the first solution, the left half. The left half in the first solution here is represented by, in the auxiliary array, the array between starting index and middle index. And the right half is, in the auxiliary array, the values between middle index plus 1 and ending index. And we're saying if the value at index I in auxiliary is smaller than or equal to the value at index j in auxiliary, then overwrite the value in main array, right? Increment I by 1 plus equal 1, else main array at index k is going to be equal to auxiliary array at index j, increment j by 1, and no matter what, increment k by 1. So here, very similar to what we did up here. And then, again, once we get out of this while loop, it means that we've either run out of stuff in our array between starting index and middle index. If that's the case, we're going to hit the second while loop. While I is less than or equal to middle index, which is what we had right here. Main array k is equal to auxiliary array I, and we increment I by 1 and k by 1. And otherwise, while j is greater than or is less than or equal to ending index, right? Main array k is going to be auxiliary array at j, and j is going to be incremented, and k is going to be incremented. Now, we do not return an array here at the bottom because we've already, we're sorting the array in the main array, right? So we don't need to return a value. And then up here, we're done. We just have to go back up to our main method here and just actually return the input array, right? And we've sorted it in place. And it's important to note here, I guess, that we call merge sort helper with the first main array as our input array and the first auxiliary array as our auxiliary array. So in the first call to the merge sort helper, when we call do merge, we pass in the main array to be the main array passed here, which is our input array. And so like the final do merge, right, which merges the top two halves of our input array, calls do merge here and overwrites stuff in the main array, right, which is our input array. And so we end up with the sorted array. This is going to run in O then log of n time and O then space. O then space being the really nice part here, because we've literally only created one additional array, the auxiliary array. And this is really like the best way you can implement merge sort using arrays. There are some other solutions that you can read about online where you can use linked lists rather than arrays, and you can actually end up with even better space complexity possibly. But those, I think, are beyond the scope of an interview. In fact, I would argue that this solution is probably beyond the scope of an interview. In an interview, you'd probably be fine with this solution. If you understand the solution very well, of course, you're in the driver's seat. You know, you're in a better place. But don't stress too much if you don't understand it. That being said, this concept of swapping values, right, like passing values that are mutable, like arrays, and swapping them in sort of recursive algorithms, are actually pretty useful to understand. You'll find them helpful in other algorithms. Another algorithm that's very famous, you can look it up online on Wikipedia, is called the Tower of Hanoi algorithm, and it's based on a sort of board game, and it uses a similar method of kind of like swapping references to arrays. Anyway, that is it for this algorithm. It was a long one. It was a tough one. Definitely make sure that you understand them, especially the first solution, but hopefully you understand the second solution as well. And with that, I will see you in the next video.